we finish this. So the main theme today is about using eigenvalue problem to solve ODE. You know ODE, right? Ordinary differential equation. A physical system involving ODE is mass spring problem. How many mass you have? You see here? Two masses. How many springs? Three springs. Okay. So this is in the the condition before the system is moving. Okay. Initial condition is like this, and then initially they are at rest. Okay, and then we disturb mass 1 by giving it an initial displacement x1. We also disturb mass 2, giving it initial displacement x2. Okay, after that, we release those mass and see what happened. What do you think what will happen? They will vibrate. Yeah, they will oscillate. But how they oscillate, we have to answer that through solving the differential equation. Okay. You see the word here, coupled. Okay. What do you know about coupling in this case? Have you seen couples? Yeah. What happened with them? Physically, what happened with the mass? This mass and that mass is coupled. Physically, they are dependent to each other. Okay. When this mass move, this mass will also move, but maybe to the same direction or to the different direction. Okay. So the movement of this mass is depending on the movement of the other mass. That is meant by coupling. Okay. How do we see coupling mathematically? Physically, is that when you see the mass being constrained with a physical object to the other mass. Okay, that is coupling physically. But mathematically, we have to see through the equation. Okay. So if this is the system, okay, we derive the differential equation, then we will arrive at this equation. Okay. This is m1 x1 double dot equal to minus kx1, etc. Okay, and this is for the mass number 2. So you have to get the free body diagram first, and then write down the Newton's second law. Okay, and then you can get this equation. But in this class, we will not ask you to derive the free body diagram. Yeah, we will only give you the differential equation, then you solve it. So we will collect the terms. Okay, where is the x1, where is the x2? Okay, and then after that, we will write this in a matrix format. Okay, writing it in a matrix format. How do we do that? The first equation is here, yeah, m1 x1 double dot plus 2k x1. So it's this one, yeah, m1 x1 double dot plus 2k x1 is this. Okay, and then minus kx2. Minus kx2 is here, equal to 0. Okay, the second equation, of course, you go from here. 0 times x1 double dot plus m2 x2 double dot. It's this one. And then the next equation, the term will be minus kx1. It's this one, yeah, minus kx1. And then 2k x2. This one. So now we have an equation represented by matrix and vector. Okay, mx double dot plus kx equal to 0. And we plan to solve this through eigenvalue problem. Remember, the eigenvalue problem has a format like this. Yeah, this is the format. Or is this form the same with this one? Is it the same format?
Yes.
Not, yeah. Okay. We don't have the double dot in here. Okay, so we need to remove the dot. the two dots, we need to remove it. How to remove it? No, we don't need self class. Yeah. Before I show you how to remove the double dot, the coupling. Yeah. The coupling mathematically is represented by this off-diagonal term. Okay. If the equation after you put in matrix and the matrix is diagonal, then the system is independent. Okay. Uncoupled. There is no coupling in the system. However, when the off-diagonal terms are non-zero, then your system has coupling. Okay. So let us remove the double dot. To remove the double dot term, we have to make an assumption on the solution. Okay. We assume that the solution to the system will be in the form of this. Yeah, x equal to v times e to the power of I omega t. V is a vector, x is this one, x is the displacement. Okay. So if I write down the x in here, x lower bar will be displacement of mass 1, displacement of x2, okay, in a vector format. And then the v in there is just coming from, actually it's coming from the eigenvector. Later on you will see that it's coming from the eigenvector. Okay. What about the omega? Any idea? No. It related to oscillation. If it oscillates, if a system oscillates, what is the characteristic you want to find out from it? Frequency. Okay. So it is the natural frequency of the system, because when the system oscillates, you want to know how many oscillation it makes in 1 second, right? So it is represented by the omega. What about the t? What is t? Time, yeah, it's time. What about I? It's the imaginary operator. Okay. So I omega t means that omega t is in imaginary number. Okay. And you know, this is the format of cosine and sine in imaginary. Yeah. Yes, it will be cosine and sine. All right. So this is the solution x1, x2 as I wrote here. Okay. And then it will be, this is a scalar and then this is a vector. Okay. ei omega t is a scalar. Yeah, you can put it on the left, you can put it on the right, same thing. And then this xi is the amplitude of the oscillating solution. Of course, it will depending on the eigenvector, depending also on the initial conditions. We will see later. Okay, now to remove the double dot again, we will continue. We take the derivatives twice so that we get the x double dot, and then substitute this into the original equation. Okay. So originally we have a system of m x double dot plus k x equal to 0, right? And then we get that x double dot is equal to minus omega square x based on the assumption. So we replace x double dot with minus omega square x. Okay. So as a result, we will have minus omega square m plus k x equal to 0.
So where is the I on the x double? Where's the I?
Which one?
Where is the I on the x double?
Oh, we are not the I, we square it. If I is squared, then you will get minus 1. Okay? Yeah. Imaginary operator I, you square it, it becomes minus 1. Yeah. It's like if you have 2I and then you square it, what's the result?
Minus 4.
It's minus 4. Okay ya, clear ya. Huh? Okay, what's the x? X is this one, right? Yeah, so this is x, right? Yeah. So it just become minus omega square x. Okay. Simply replacing V e omega t by the x. Okay. Yeah, any other question on this? Okay. So we can, as suggested by the slides, if we multiply the equation by m inverse. Okay. If you multiply by m inverse, all of them from the left side, and there is a scalar only in here. Yeah. This one will become identity, right? Okay, identity. And then let me just write it here. So let us multiply by m inverse plus m inverse. Okay. Yeah. So what happens if I multiply with this identity? Yeah. So it just become minus omega square x plus m inverse kx equal to 0. Okay. Then I move it to the right side. I move this to the right side. Finally, I will have m inverse k. Alright. Now this have the same format as what? Ax equal to lambda times x. Same, right? So what's the A in this case? M inverse k. What is the lambda? Omega square. Okay. So if you work in this fashion, you can find out the omega by finding the lambda. Okay. Question? Alfred? Michelle? Okay. Johan? Yeah, Ryan? No, of course not. You, in the test, you will be given the differential equation scalar format, yeah, and then you have to form the matrix like this, or yeah, if there is no double dot, then you just form the matrix as it is. Okay. And then you need to find out what is the A matrix, what's the lambda in that case. Okay, no need to derive this one. Yeah. Which one? This whole thing. Okay. The x in here is the displacement of the two masses. Okay. We are still talking about solving this. Yeah. So the first thing, we derive the differential equation. Okay. We want to solve the differential equation, and then the solution will be the displacement of the mass 1 and mass 2. Yeah. And the displacement of mass 1 and mass 2, we denoted it as the x in here. Okay, and x is here, x1, x2, displacement mass 1, and this one is displacement mass 2. So we assume that the displacement is V times E omega t. Okay, and then we derive it. We take derivative with respect to time twice, so that we can get the format of x double dot. Because initially our equation is this one, right? M x double dot plus kx. Because we want to get the format of ax equal to lambda x, we want to convert the x double dot into x, right? So by deriving it twice, we can get x double dot equal to omega times x, omega square x. So that means by replacing this into x double dot, we get the x term only in that case. Okay. So to construct the solution, we need two things in there. Yeah. The first thing is the omega. Omega is the natural frequency, and that is coming from the eigenvalue solution. Okay. Omega square is lambda. So once you get the lambda, you take square root of it, you get the omega. Yeah. And then the second component of the solution is the V. Okay. So the V later you can get it by using the solution of lambda to get the eigenvector. Okay, that's the V in that case. Okay. Is this clear? Okay. Okay. So if I continue, we know that the x in there is V E omega t, right? Okay. So I'm continuing from here. X is V E I omega t. Okay. E omega t here, left and right, these are scalar. We can cross them out. Yeah. Correct. Scalar, cross them out. Is that clear? Okay. Yeah? And so we are left only with this equation. So I can replace the x with the v in that case. Is this clear? Alfred, is this okay? Alfred? Huh? Digesting. We just express the. Okay. Let me write down here. Yeah. So from the previous slides, the equation is okay. Now we replace x with the v. Okay. This is v. Yeah. Okay, we can write because x is this one. Omega square. Then okay, like that. Agree, everyone? Agree, yeah. Now this is a scalar, yeah. E I omega t is a scalar. I can cross them out. Yeah. No objection, right? Can remove this. So my final equation, M inverse K. Yeah. So that's the final equation. And then if you write down in the usual eigenvalue problem, it will be like this. Okay. So if M is a diagonal matrix, what will be the inverse of it? M is a diagonal matrix, right? Now, the inverse is this one. Yeah. You take 1 over M1 and then 1 over M2 as the inverse. Symmetric, yeah. Diagonal. Diagonal is symmetric. Any problem on this? No. Okay, let's move on. So now we are in our territory already, yeah. The territory in eigenvalue problem. Okay. So where's the coupling? The coupling is in here, yeah. Off diagonal terms, non-zero. Okay. Off diagonal term, minus k over m2, minus k over m1, non-zero, so there is a coupling in there. Okay. Rewrite this equation as that one. Then you will get the usual a minus lambda I. Okay, and this will be the eigenvector. So you find out the eigenvector and eigenvalue of this problem, you can solve the mass spring systems. Agree with me? Yes. So the trivial solution to this is that x1, x2 to be 0, yeah? But that's trivial and that's not useful. We have to find non-zero solution to the x. So once we are reaching this, then we are actually repeating the process of finding eigenvalue, finding eigenvector of the matrices that we discussed last week. Okay, so there is no difference on it. So what I introduce you today is just to bring you from the ordinary differential equation in matrix format, we bring it into the eigenvalue problem here. That's the only additional thing that we discussed. The remainder are the same. Okay. So for this, let us solve it. If you want to find out the lambda, remember we have to find out the determinant of this. Yeah, determinant of this is 0. We know it is 0, but we have to express or expand the determinant equation of this matrix. And so because this is 2 by 2 matrix, what's the determinant? The top left multiplied by the bottom right minus bottom left times the top right. Okay, then you will get this. And so finally you get the quadratic equation on lambda. So the roots of this will be the eigenvalue of the system and also the omega square, yeah. The lambda is the omega square. Remember, lambda is omega square.
Atau lambda was omega.
No. Lambda is the omega square. So once you get the lambda, you have to square it, not square it, take the square root of it.
Let the lambda take the square root.
Yes.
So to get omega.
Yeah, to get the omega. So from here we know that lambda is the omega square, right? What is the omega then?
Omega is
Square root of lambda. Okay. Yeah, Brian. Say that again. Omega square is what? For what? Oh, you mean for this kind of system? And then what's the question again? Yeah, if the solution, if your problem is only the x dot, yeah, then it will be different. Yeah, it will be different. Let us finish this one first, and then we can get it into different type of problem. Yeah.
Okay, so
For example, of course, I want to give you this example. this one only, yeah, x dot x double dot, this is k, this is m. So the solutions ODE will be what? It will be mx double dot plus kx equal to 0. Still x double dot, right?
Yeah.
But I can write it down, define the state space. Remember when I teach you dynamics and MATLAB, x1 is x, and then x2 is x dot, and so I will get x1 dot, x2 dot, 0, 1, 0 minus k over m, x1, x2. So this is in the x dot format, yeah. And then there is another also a solution from here, for which if I give you the, let's say if I give you the solution, okay, x1 t is equal to something, x2 t is equal to something, yeah. And then if in here you will get the lambda in there and then the eigenfactor in there, okay, your job is just to find out what's the eigenfactor of this matrix and also the eigenvalue of this matrix, and you put it in the equation. Okay, so the process from here up to the solution is not your part. Okay, your job is to find out this format from here, yeah, finding this format, and then finding eigenvalue and eigenfactor of this, you insert it into the solution. So the solution, we will give it to you. You want to get it from here to here. Okay. So if I take x1, take the dot, it will be x dot, agree? Yeah, and it will be x2. Same, yeah? And then after that, I will just express this equation, x double dot. What is x double dot in here? It will be, if I take the 2 dot here, I put the 1 dot here, right? Agree?
Oh,
Agree, yeah? So now I can write down mx2 dot plus kx1 equal to 0. Agree with this? Yeah. So I'll just express what is x2 dot. It is minus k over m x1. No, I move it to the right side. Yeah. Really? Understand? So I will now express this equation into matrix format. Okay. Suppose you are given this equation and you put it into matrix format. Can you do it? 2 dot. Okay. x1 dot is equal to what number I have to put here? Use this. x1 dot is equal to what? What number I have to put here? Here. 1. 1 means x1.
oh,
X2 is here. 0. Here. I'm using this equation. x1 dot is equal to 0 times x1 plus
0 times x1
times what? 1. Yeah, 1 x2.
1 x.
What about x2 dot?
over
One
M.
Oh yeah, it's here. Yeah, sorry. Just now I made a mistake. And then it's 0. So like that. Is this skew symmetric matrix?
No.
No. Okay. Unless k and m you divide it become 1. If k over m is -1, then it is skew symmetric. All right. The solution to this, if this is x dot equal to ax, yeah, the solution to that is, do you know from the differential equation what's the solution? Okay, that's E80 x0. How do we find out E80 x0? Okay, good question from Brian. Now I explain some discussion in here. So E80, this can be rewritten as, pay attention.
Sine.
No, this is an exponential matrix. Okay. Yeah. What is L? What is R? Anyone know? This is the left eigenfactor. That's the right eigenfactor of the matrices. Or I can also write it down as capital X inverse. So you diagonalize the system. Okay, using the diagonalization method, we can diagonalize the A, then you get the term. Okay, so this is the eigenfactor. This is lambda 1, and this is the second lambda. Okay. So you are still finding out the eigenfactor and eigenvalue also in this case. Okay.
What is that notation mean?
The what? This one?
Yeah.
So that is the diagonal of the matrix. Eigenvalue, you put it on the diagonal. Yeah. Okay, so let's say you are starting from here, yeah, Brian. Starting from x2 dot and x1 dot. We don't have the double dot, right? Yeah, you end up with this. One of the solution is like this one. Okay. You still have to find out eigenvalue and eigenfactor. Okay. Right, let's move on. The thing is that we have to find out the lambda, yeah, and you can use the method directly, the ABC method, ABC formula. But in this case, the slides multiply the equation by m1 times m2. Okay, sorry, where is it?
The lambda is a function of the M.
Yeah, lambda, of course. Okay, k, m1 and m2. Yeah, so when you are given the value of m and k, then you can get the solution to the lambda. After you get the lambda, okay, suppose m1 equal to m2 to simplify the equation.
Can we do this next step?
Huh?
Can we always do this?
The exam shouldn't be too complicated. Yeah, shouldn't be too complicated. Should be, yeah, not so complicated. Should be, yeah. So it will test your understanding to get the eigenfactor, eigenvalue, and use it to get the solution. Okay, so let's say m1 equal to m2, then your lambda will be k over m and 3k over m. Okay, then what's the omega again in this case?
Omega.
K over M.
Yeah, square root k over m, and then square root of 3k over m. Omega, you take square root of the lambda, ya.
Lambda. We still in the same.
Don't square it, square root it. Okay.
Square.
Now, to find out the eigenvector, how to get the eigenvector? Substitute the lambda into this equation, find out x1, x2.
Substitute the lambda.
Yeah, just like how you find the eigenvector. This is your lambda, right? K over m. You put k over m here, here, and then get the solution. Yeah, let us try to find exercise. Let us do an exercise.
Exam, can we just expand the equation of x1? Just the ratio or
Yeah, you give the ratio, of course. What we want to find is just the ratio. Yeah, you remember the eigenvector is just the direction. Okay, so the ratio is enough. Okay, we don't need the exact value of it. 2k over m minus k over m, and then minus k over m, and then in here x1, x2 equals 0. Let us use the first one only, yeah. Okay, so we have what? 2k minus k become k over m, yeah.
Yeah.
x1 minus k over m x2 equal to 0.
So where do we get the 2k over m minus k over?
From here, right?
Oh.
Or do I have to write everything? Oh, okay.
So I mean, where does the equation come from?
Okay, let me write down from beginning, okay? Minus lambda this one. Your question is this one or my writing just now? This one?
Okay.
That is the equation of m inverse k.
Oh.
Okay, m inverse k is the previous one, m inverse k x1 x2 equal to 0. The original one. So let me go back. Okay, this one, which is this one.
Oh.
Okay, because m1 and m2 are the same, so this. Okay. What about the minus lambda? You know where it comes from? It's coming from here, yeah.
A minus lambda.
Okay. So let us solve the eigenvector now. Okay. A bit delayed. Delayed. Okay. Put the lambda equal to k over m. Okay. Now I put the lambda equal to k over m. Remove this. Put k over m. What is x1 and x2 in this case?
K over M.
Berarti k over m minus k over
So
minus k over m.
in that case, x1 equal to x2. In this case, the b1 is equal to x1 1 1.
Oh, okay.
Okay. Any question on this? Yeah. Yes.
What does
Say that again. What does?
what?
Okay. So that one you can actually replace with any number. Yeah. So alpha 1 is a real number.
If velocity is
Okay. Okay. So x1 and x2 is the solution for lambda 1, and that one is 1 1. And the direction 1 1 we can multiply with any scalar on the left side. You multiply with any scalar. So I put alpha 1 in here. But don't put nothing in here. You have to put something in here. Okay. Yeah, any question again so far?
so why is it k over mx1 minus k over mx2? It's k over mx1.
Okay, that's
I'm using the top one.
Yeah.
2k minus k is here, right?
oh,
Yeah, okay.
you see
Okay.
the second one, sir. That's why he was-
Yeah, the second one is also the same.
Yeah, the same.
Example,
Yeah, you can use the first equation or the second equation. Choose one of them. One of them is enough. Okay.
K over M itu lambda ya.
K over m is the lambda.
Ada dua lambda.
Of course, the first lambda you get the first eigenvector. Put again the second lambda, you get the second eigenvector. Okay. Yeah. So let me do the hard work here. I'm writing again the second eigenvalue here. Yeah. I hope with this you can clearly understand what's going on. Now let's do for the second lambda. Ready?
Yeah.
Yeah, second lambda minus 3k over m. Then minus k over m. Then 2k. Okay, where's the lambda here?
K over M.
Okay, that's the lambda. Okay. So the equation becomes minus k over m plus, not plus ya, minus.
Minus K over M. Berarti kita dapat sama posisi.
So now we know that x1 is equal to minus x2. Okay.
Yeah.
So in this case, our second eigenvector, sorry,
1 minus 1. Alpha 2. 1 minus 1.
1 minus 1. Okay,
Minus 1. 1.
they're the same, right?
So if I write it 1 minus 1 is
The same. Yeah,
minus 1 is 1 and 1 1.
the same. Same direction.
As long as one of them is minus.
Or, yeah, as long as one of them is minus, one of them is plus. Now, where does this located at? Plus and then minus, so it's going this way.
Balik.
It's going this way. Okay. What about the first eigenvector? It's this one.
Yeah.
Okay.
In the real life case, what would this?
Okay. For the first eigenvalue, which is k over m, the movement are the same, yeah. Mass 1 move one amount, mass 2 move one amount. Let's say 10 centimeter to the right, the same. So like this. at that frequency. But if the system is moving at this frequency, 3k over m, then they will do this. Okay. And what is the true solution then? The true solution is the combination of these two. Okay. So if I write down the solution, let me write down the solution here. Yeah. It will be the combination from the two. Yeah, the solution xt, it will be c1 p1 bar e I then square root k over m times t, like this, yeah, plus this is c2
This 3k over.
okay. V1 is that one, yeah. V1 is this, V2 is 1 minus 1 or minus 1 1. What about C1 and C2?
Alpha.
No, that's not alpha. C1, C2,
SK over.
find them from initial condition. Yeah. From initial condition.
Oh,
What's the initial condition? X1 0. Okay. X2 0 and then X2. From this. Huh? No. What does it mean? X1 0 is X1 when t equal to 0.
Yeah.
So they are not always 0.
Oh. Kan bisa ya X0 sama dengan
What happened when these are all 0?
when all of that are 0.
What happened? It's not moving. No problem.
C1, C2 will be X1.
No, of course not. No.
So there will be a case where V1 is like 1 and 0. The alpha times 1 and 0.
That it can be if the system is uncoupled. Yeah.
Yeah.
Uncoupled,
Oh.
then it is 1 0 0 1. Okay, it's uncoupled. You have two masses, all of them connected by spring. One of them you hold it.
So if you only got C1 and the question is coupled, then I must be wrong with it.
Yes.
You are wrong.
Another example is like this.
Wow.
One couple.
Uncoupled
Yeah, this is uncoupled, of course.
with the connection.
It is just a two system in the same whiteboard. Okay, they have no relationship at all. Are you in a relationship? Right? No. Is this coupled?
No.
Independent.
No, not coupled. Yeah. Physically, they are not coupled. Mathematically, you will also find that these are not coupled.
So, every time we solve ODE, we must using matrix. We must add like C1 times our answer.
Yeah.
Times.
Yep. And the format of the solution will be given. Yeah, we are afraid that you will get lost here. Okay. We know that you will get lost when getting the solution. So your job in here is to find out what? The V1, V2, omega 1, omega 2. Okay. C1, C2, no need.
But then we write the V1 as that.
Yeah, if you are asked this and then you are given this, then you have to find C1, C2.
Oh. Also, we have to write the V1 as alpha 1 at x1.
Wala, kaya gimana?
Ya, tinggal
Easy accept dan lain. Tahu V1 itu juga.
harinya baru.
V1 itu udah dapet.
Yeah, actually, sorry, C1 and C2, this is a vector also, yeah. This is a vector. So you have four unknowns and then 4 variables in there.
Yeah.
How many equations that you can get from here? How many equations? You have 4 unknowns, right? How many equations? How come it is 4? You need 4 equations. The first one is the displacement. Yeah. You have x1 and x2, so 2 equations. Okay. And then you take the derivative of it, get another 2 equations.
Karena x tentu.
Okay. Oh, let's move on. So the same thing are explained already, yeah. So this is omega 1 and omega 2. An example. Okay, now we go example with numbers, yeah. If this is the mass, that's the K. What will be the omega and then yeah, this is the omega. Okay. So 40 kg, 2K.
Wait.
That's too fast, yeah. Okay, coming from here.
So it's basically 10 minus eigenvalue.
Yeah, how do we get the 10 in there? How do we get the 10?
Given.
What? 10 minus?
Okay, remember again the form is this one, yeah. This is the form.
Okay, so this is applicable for any spring system.
No, only spring system that is connected like that. Okay.
Extend the K over M. Then minus
So you cannot
lambda
relate
square.
it.
So we have the 2K minus lambda. This is minus K over M2. 2K over M2 minus lambda. Okay. Then x1, x2 equal to 0. So the problem here, mass is 40. Yeah, both are 40, K 200. So 2 times 200 divided by 40. It's 10. Easy, yeah, it's 10, yeah. 400 divided by 40.
400 divided by
10.
Astaga.
400. Oh, 400. Another 200.
Are you awake, Alfred? How do you get the 10, you know? Insert the K and M here. What about the 5 here? Yeah, 200 divided by 40. So it's 5. Yeah. What about this one? 200 by 40. The 10 here? The same thing, yeah. 400 by 40. Why is it omega square, not lambda like this?
Lambda is omega square.
Okay, now you know, yeah, okay. Okay. Awas kalau salah ya.
Awas. Salah biasanya kalau
Exam bakalan spring juga.
I don't know. I cannot answer. Okay, now you get the roots of this characteristic polynomial, you get the omega square. Okay.
Oh, okay.
Wait. What's the square root of this? Yeah, yeah.
3,87.
No. Get your calculator.
What you mean?
3,87.
Kok bisa 3?
Is it?
3.87.
Okay. The unit is not hertz. Okay, radian per second. It is radian per second. Yeah, that's mistake. It is straight coming from slides.
Momentum.
Unit is radian per second, yeah, not hertz.
Ya, pentingkan ya.
Main bisa nyari periodnya.
You see, okay. Now,
Malah, weh. Kok jadi frekuensi?
you get the period here. Yeah, which is why that one is in radian per second. Okay,
Yes.
which is why the 2 pi divided by this is correct. Okay, this is correct. But just now the unit in here is radian per second. Okay. Now we want to get the V1 and V2. You just substitute the omega, yeah. So this over here somehow it's not related lah. Yeah, not so related. It only want to find out the period. And then how you get the eigenvector is just this. Okay. So it is always 1 1 and 1 minus 1. Whatever mass you have, it always like that.
Why are they putting?
Sorry?
Why are they putting?
They're using one.
Oh, we want to normalize it so that the length is 1.
Why is it minus?
Normalize.
Yeah, normalize. You remember the drawing I put there? 1 1 and minus 1 minus 1. Are they the same or not?
Jadi jawabannya ini, tapi kita normalize.
No, you can normalize. Whether you normalize or not, that's the same. It will only affect the value of C1 in here. Okay. What
Itu mungkin norm equation.
for the eigenvalue? Sorry, for the eigenvector, you can either normalize or not. That's the same eigenvector.
How to normalize?
Normalize.
Equationnya jadi satu-satu.
You divide by the norm. Okay. V1 divided by the norm of V1, you get the normalized eigenvector.
Satu sama negatif.
Okay. Let's see again. Let us see the 1 and 1. Yeah. Just now we get 1 and 1, right? Yeah, 1 and 1. So we do this. 1 1. Yeah. What if I get 0.5? 0.5. The same, right? So the 0.771 must be here, right? Yeah. Or in here, if it is minus. So it's the same. Okay. Alfred, Michelle, is it okay? Yeah. The 1 1 and minus 1 and 1, it can only happen when mass are the same mass, same k. Okay, if mass 1 mass 2 different, then this number could be different, but they will move at the same direction. Okay, let's say mass 1 is 10, mass 2 is 100, like this. Okay, no, not like that. Yeah, the first eigenvalue or the first natural frequency, they still move at the same direction, but then different magnitude. In this case, 1 to 1. Yeah, in this case it could be 10 to 1 or 5 to 2. I don't know. Yeah, depending on what the value of k. But for the first natural frequency, direction is the same direction, different magnitude. Okay, but for the second natural frequency, they will move in the opposite direction. This. Yeah. Any issue on this? It's okay?
Saya next.
We get the value of x1.
No need.
Huh?
We don't have to find out. We don't need the exact value of x1 and x2. We only need the ratio. Okay? For eigenvector, what you need is just the ratio. If you find out the exact value of this, then you will get only a point, not a line. Okay, eigenvector is a line like this. Yeah. Any other question? Yeah, the exam will be on this. Okay, so I hope. Yeah, question number 3 for the exam will be about solution for ODE from eigenvector. So if you get lost today, then goodbye. Really?
Belum, bro.
I don't know what happened. I'm trying my best to explain about this. Okay, if you somehow get lost or you don't pay attention, then yeah, it's your call, not mine. Yeah.
We study problem.
No, not enough. You have to understand first. Okay, understand the concept first, and then you can study after that. So don't come on the day of the exam without understanding the concept. Do anything you can. You can ask me again, or you ask anyone. Don't have to be me, right? Okay, this is just a visualization for the first mode. Sorry, this is wrong. For the first mode, move the same direction. Yeah, this is the first mode. Same direction moving. Okay, and this is for the second mode. Different direction moving. Same magnitude. Okay. So this is a mistake. Any questions? I put another example here. Actually, the same example.
Will I need us to make a graph?
No. I don't think so. Another example also given in there. Yeah. So you can study the example. Okay, what's your idea? Let us see this problem. What's your idea, Ryan? Michael? Radit? Alfred? Yeah, Delon, you know something, Delon?
No.
Rafi? Your idea? The keyword is symmetric and then orthogonal. Yeah, so you have to use the symmetric matrix properties, which is the transpose is itself. Yeah. So how to use it?
Times the matrix equals 0 orthogonal.
No.
So that eigenvector of symmetry correspond to value.
Let's say a matrix A is symmetric. Okay, so its transpose is equal to itself.
Yeah, right.
And then its first eigenvalue can be found out by solving this equation. Correct?
Yeah.
Yeah. And then the next eigenvalue, different one, yeah, we can get it using this. Okay. Of course, when we get a different eigenvalue, different eigenvector, right?
Yeah.
Stating here different eigenvalue, yeah. If you get different eigenvalue, then eigenvector will be different or symmetric. Then what I will do to here is that I will pre-multiply on the left side by the transpose of x2. So I will do x2 transpose. Okay. Any objection up to here? Huh? Why? Now, the step is something that you have to think on, but yeah, but we want to show that this is equal to 0. Okay. Well, what is the orthogonal mean here? Orthogonal means the dot product 0. Yeah. So you have to use the property of symmetric matrix, which is this one, and then different eigenvalue. So we have these two different eigenvalue, and then we also have to use the orthogonality property, which is dot product of the two eigenvector 0. So it is natural that I want to multiply this eigenvector with the transpose of the different eigenvector. That's natural. Yeah. Okay, and then the next step, I have to use this property. How to use this? From here, I want to use this property. Any idea?
Change the A to 80.
How to do that? I cannot just change, right? What's the operation that I have to use here? To get the A transpose, what's the operation I have to use here? We take matrix, we take the transpose of what? The whole thing, correct? That's a good idea. Take the transpose of the whole thing.
Oh wow.
Okay. Why do we have to do on the whole thing? Yeah, because that's the fair thing to do, yeah?
Fair.
Mathematics has to be fair also. If you are not fair, we cannot move on. We only do transpose here, not this one. No, that cannot work. Okay. Also, multiply on the left side with this. Also on the right side, I have to multiply. That's fair. What happened with this then? It will no. This one first. It will be what? X1 transpose times A transpose times X2 is equal to okay. Still lambda 1.
Oh,
Lambda 1 is scalar.
X.
Lambda.
X1.
That's lambda.
jangan scalar.
Now he thought it is a X, yeah. Looks like an X.
Looks like an X.
Okay, that's lambda. Okay. From here, what we need to do?
Find the eigen.
No. Yeah. It is scalar. Which one?
Iyalah.
This one? Matrix. This is a matrix. If it is, what do we need to do?
20 times x.
Use this property. Substitute what? 80 with A. Correct. Okay.
Adil.
What's the next step? What's the next step? If we use this, then what happens? Yeah, substitute AX2 with that one, yeah, lambda 2 x2. Okay, what's next? How come we cancel? We cannot cancel. If it is scalar, we can cancel. Okay, now I have the term like this. Sorry,
Zero.
lambda 1. Okay, now what's the last property that we will use here? The last property from there is
Orthogonal.
Different eigenvalues.
if it is different, then the only solution to this is if lambda 1 and lambda 2 are different, then the only solution to this is which one is 0? Okay, x1 transpose x2 must be 0. Yeah, that's the only solution.
What different?
You don't understand? Okay, that's the key line, yeah. Okay.
Oh, karena dia zero berarti ortogonal gitu ya?
Ya iya.
Oh iya.
Of course. Since lambda 1 is not the same with lambda 2. Ya kan different, right? Then x1 transpose x2 equal to 0 must hold. Okay. So after that, we know that eigenfactors for different eigenvalues are orthogonal. So this is how we show it. Okay. Yeah, if it is not 0, then there is no solution to this. Except when lambda 1, lambda 2 are the same, then yeah, it's different thing. Okay. It is saying for different eigenvalues. Okay. Oh, it's clear. So we are off the time already. There are actually some other things that we can still discuss if you will stay here. It is up to you. I can discuss this spectral shift, scalar, raising to power, eigenvalues of the inverse, this one, that one. Yeah. Should we continue up to 10 or you want to leave? Up to you.
Continue, sir.
What? We just discussed it. No, I mean the example that we discussed just now. That is like the exam. Yeah. You need to find out eigenfactor, eigenvalue, put them into the solution. Like that, yeah.
Example apa? Problem 1, problem 2 buat exam sir.
It's like the quiz.
Kita discuss ini lah.
The quiz is next Thursday.
The quiz Monday 29, right? Tuesday.
Oh, the exam is Thursday next week.
Tuesday. Oh, the quiz Thursday.
Ini exam dulu baru quiz.
Quiz dulu.
Quiz first.
Quiznya itu this Thursday.
Yeah.
Examnya next
Okay.
Tuesday.
So for the quiz on Thursday, I will give you problems for number 1, 2, and 3. Yeah, I mean the concept are similar, so that you can get the feeling of doing the exam on Thursday. Okay, you try it first, and then we discuss. If I explain here, you just like watching YouTube. I don't think it will get into your head. You try first, yeah. Try. Yeah, this one is better to discuss because it is related to the concept. Yeah, you need the concept to solve the problem. You need it. Okay, any idea to show the spectral shift?
Just circle.
If we shift the matrix by A minus Ki, then eigenvalue will be this one, and then the same eigenfactor.
This show, bro. Bukan
No, we have to show. This is true. We have to show.
False.
We write down the
Aduh, kenapa proving lah ini?
I think we should write the A like as a
Kadang,
times to
bro.
matrix plus A1.
What if we write down like this, like this one?
Okay.
Okay, we know that in this case the lambda is the eigenvalue to A, right?
Yeah. Then we shift the A to A minus Ki.
Yeah, if we shift the A minus Ki, let's say this is V beta times V lah.
To show that X is
Yeah, we have to show that beta is just lambda
plus
minus K. It's lambda minus K. Okay, what's your idea? Let's think of an idea.
and we substitute the lambda.
Substitute the lambda into what? To here, yeah.
Yeah.
So let's say if we have this, substitute this into here, okay, lambda minus K times V, then we take out everything, AV minus KV, this lambda V minus KV. So that will give you the AV equal to lambda V. So that means eigenfactor is the same with this. Yeah.
Yeah.
You just plug in here, replace it.
False, ya guys.
There is no true false. You have to show.
So what is the identity math?
Huh? What do you mean? Here? K times I times V. I times V what? What is I times V?
K but in a I size.
Yes.
Yes.
K in the I size.
Yeah, what is KI? KI is identity. Yeah, and then the remaining diagonal matrix plus all are 0. That's a KI. The identity is gone here, right? Become just KV. Huh? Identity times a vector is a vector itself. So this is just like a number 1. 1 times something is that itself. Okay, what about the scalar multiplication? What's your idea?
You bukan pernah dibahas.
Yeah, if it is something that has been discussed, then what's the answer?
Apa answernya?
Ready? 27. Come on.
True. Pasti true.
It is true. What's the proof of it?
Absolutely. AX equals lambda X.
Ya tinggal tambahin K doang sih.
Point K ke lambda,
Yes sir.
ke A dan lambda.
Ya tinggal K KAX equals K lambda X.
Iya.
Yeah, of course.
K-nya dihapus gitu. Kenapa?
Kan harus
This is easy because you multiply all of them by A ya.
harus fair guys semuanya.
Multiply.
Sama kalinya tapi kayak gitu.
Okay, so in this case, this is the new matrix and this is the new eigenvalue. Okay, same eigenvector. What about raising to a power?
Ada eigen. But if we write it like that in homework, we will get full score.
Yeah, of course.
But why do you write the K on the second one? It's in the middle, not on the front.
Because it's scalar. Oh yeah, to be fair ya. Okay.
Like, is there like an order we need to follow? So, I was
Yeah,
thinking that.
okay.
Is there like an order? Like,
Yeah, I agree. So that's K lambda.
So that's
just
it.
making sure.
Delta I.
Iya. Kan diberikan ke sama dengan dia kali.
Dipangkatin semua gitu kalau ini sekarang. But the eigenvector is changing.
How do we know that it has the same eigenvalues with it? Same eigenvector.
But if we power of them, the power of 5, then the enggak.
Oh.
Now, if we power it, let's say
X-nya juga
ax,
berubah dong.
we square it. Okay, and then we square. What will happen is that you will have ax multiplied by ax equal to lambda x. We cannot, of course, wait, what if we square it? If we square it, we don't do this. Yeah, sorry. If we square it means we multiply from the right side. Yeah, it's from the right side, is it? So this will be so I will multiply. This is my original equation, okay, and then I pre-multiply all of them by ax from the left side. So I will have ax lambda x like this.
AX.
Yeah. Okay, this is my original equation. Yeah. Now, based on this, then I will have ax. What's my ax here? Is my lambda x.
Oh, then.
And then in here I will have my lambda x again. And then here lambda x.
How come so? Bisa gitu. Gimana?
No, it's not canceling out. Wait.
Jadi x pangkat 2 sama dengan lambda square x pangkat 2 gitu.
No, because ax square is that I multiply this ax by this ax too.
Okay.
No, we cannot do that. Sorry.
Cannot do that.
Sorry. Yeah. I think I made a mistake here. This one is a vector, right? This one is a vector, so we cannot square it. We have to multiply by its transpose. I think I have to isolate the... Oh, okay. Now I know how to do it. I see. I can diagonalize the matrix A by having
Harus
by this, yeah. So this is the eigenvectors, and so my D in here is x A x inverse. So in this case, D containing all of the eigenvector of A, like that, yeah. So I'm doing the diagonalization in here. Then I can take the power of it. Okay, because D contains the eigenvalue of A. Now I can get the power of it. Let's say this is D to the power of M, then it will be to the power of M. Okay. If on the left side I take the power, on the right side I also take the power. Okay.
How you get the first eigenvalue 1?
This one? Now I diagonalize matrix A into here, yeah. If I do the coordinate transformation, and this is the eigenvectors of A. Remember we discussed diagonalization last week. Okay, I can get a diagonal matrix, and the diagonal entries are the eigenvalues of A. Okay, so in here I diagonalize A using eigenbasis of A. Yeah. Are you opening MATLAB now? No.
Oh,
But you can try. So this relationship showing that if I have the set of eigenvectors of A in here, re-multiply left and right by the eigenvectors of A, I will get the eigenvalues of A in here. Okay. Now, because I need to show A to the power of M and lambda to the power of M, I have to do this. And then what I can get here is that lambda 1 square of M, lambda 2 square of M.
yeah.
So this is the situation. Okay. Yeah, if I take the power of the diagonal matrix, then it will be diagonal matrix and the entries is just the power of it. Yeah. So what happened with this? The power of M. Then I will get x A x inverse multiplied by the same thing, right?
Alright.
X A x inverse. What happened with this?
It
Huh? X inverse times X.
A
X inverse times X. I. Identity.
A. Jadi A times I.
Yeah, it becomes identity, right? So you will have identity times A, and then in here we all have identity. Okay, and then identity times A, which is equal to X A to the power of M X inverse. Yeah, so this means that if we have A to the power of M, then the eigenvalue will be lambdas to the power of M. What about the eigenvectors? Same eigenvector. Okay, so this is how we show it. So just now the method is wrong. Okay. Yeah, X inverse times X. Yeah, we have to multiply all of them. Okay, an example is this. I'm showing you an example. XA X inverse to the power of 3. Yeah, it will be
X A X
multiplied by X
inverse X
again.
Yeah.
Yeah, so the result is
X A identity.
this is identity.
A
again. This is identity, right?
X inverse.
X. No, identity A again. X inverse.
Yeah.
Okay. So this become identity, and that one become identity here. Yeah. So the result done. Yeah. Okay. The next topic is about
trace.
Yeah, you can use any matrix to show. So you just assume you have a 3 by 3 matrix and show it. In this case,
Trace of matrix A is not
it's the sum of the eigenvalue.
The trace of A equals the sum of trace of A. Suppose we have 1, 1, 1. Is it the magnitude of the value or the jumlah?
Yeah, for example, if I have like this, yeah.
So the eigen is 8.
Yeah, lambda 1 is 1, lambda 2 is 2, lambda 3 is 5. Yeah.
Or the sum of the
summation of AII is 1 plus 2 plus 5, 8. And if you sum lambda I, 1.
I thought we will have 8 eigenvalues.
No. Okay.
Yeah.
Okay. A inverse exists if and only if eigenvalue are all non-zero. How to show?
Kalau itu harus singular kan ya?
No. A must be non-singular.
Yeah.
A inverse exists. This is non-singular.
Singular ya.
what is the equivalent condition for A inverse exists?
Determinant not zero.
Ax equal to 0 if and only if x equal to 0, ya. Yeah. Determinant of A is non-zero. Okay. If this exists. So if you have the eigenvalue problem where A minus lambda I 0, we want to show that if lambda equal to 0 is a solution, then it will come into contradiction. Okay, let lambda equal to 0, then Ax equal to 0, right? So the only solution is x0 because A is non-singular. Exists, right? A inverse exists. The only solution is x0. So this is a contradiction. Can't happen. No. Okay, let me repeat again. We want to show that if this is true, then this is all non-zero. Okay, the statement says it says if and only if, right? Okay. A inverse exists. It implies lambda I non-zero. Then if lambda I non-zero, it means A inverse exists. So we have to show both ways. This one resulting in this one resulting in this. Yeah. Now I will show this one first. If lambda 1 non-zero, it will result in A inverse exists. Okay. And I will show by contradiction. How to show by contradiction? We put something that contradicts this. What is the contradiction to this?
If lambda 1 is not.
If the lambda is 0, right?
Yeah.
That's the contradiction. We put the lambda 0, then we will find in this one does not hold. Okay, so that means the inverse exists for lambda non-zero. Yeah.
Jadi kalau lambdanya equal 0, itu jadi A-nya nggak exist.
Yes. It is shown by this. Yeah, the only solution to this is when x is equal to 0. So when lambda is 0, mean we can find x non-zero to solve this. But because the system is invertible, this one contradicts. Yeah, you put here, then you will find contradiction. Okay.
The inverse of the x.
Yeah, the A inverse has the eigenvalues of 1 over. That one we haven't shown that yet. We haven't. Try using the 2 by 2 first, and then 3 by 3. Yeah. What about we show from A inverse exists and this one to be non-zero? How to do that? Yeah, this one from lambda 1 0, we arrive at A inverse exists. If and only if means we go the other way around, both ways. Okay, now the sufficient condition A inverse exists, we reach that lambda I cannot be 0. Okay, so when A inverse exists, means determinant A is non-zero. Okay,
Yeah.
so when we examine this equation, yeah, determinant A non-zero, it means that lambda cannot be 0 for this. Yeah, because A inverse exists, it means determinant A is non-zero, and by observing this equation, determinant A non-zero, it means that the lambda cannot be 0 in this case. Because when lambda is 0 in this case, that means determinant A is 0.
But how can we prove that determinant by the equation?
Now we are assuming, because from this assumption, yeah, we want to show that when this true, this must be true. Okay, so we depart from here. Because A inverse exists, then it means determinant A non-zero. Okay, then we observe this eigenvalue problem. If determinant A is non-zero, then lambda in this case cannot be 0. Because when we put lambda equal to 0, then determinant A equal to 0.
Yeah, but we prove that if we put lambda equals to 0 using that equation, and then we work on the equation, find the determinant is 0.
No. We go from here, then get the lambda. When we do the lambda non-zero, we go here, we do this just now. Yeah, we do this. That is the if and only if situation. You put lambda equal to 0 first, you get contradiction. Yeah, that's the contradiction. Right. This one gives us the if and only if proof. Okay. What about the eigenvalue of the inverse is 1 over the lambda? Any idea on this? A inverse eigenvalue is 1 over lambda.
Yes.
Okay, you now just now you see diagonalization of A.
So
This one,
inverse
yeah?
all of them.
Huh?
We inverse all of them. No.
We have to show that D inverse.
Nah, yeah, betul.
Yeah, that one. We take the inverse of this.
Yeah.
Okay. We take AX A. Take the inverse on left side, take the inverse on the right side. So this one is just what? 1 over lambda.
Lambda.
So you know how to do it now, yeah? 1 over lambda 1, 1 over lambda 2. Okay. Why I draw lambda like X, yeah? Sorry. This is a habit. Okay, what happened with the inverse on the right side?
Yeah.
What does it become?
A inverse times
Nah.
identity.
It becomes X A inverse times X. You remember the inverse of the product, you flip the order. X inverse.
Yeah.
Okay.
We flip the order, yeah.
Identity dong.
Not identity. We are not doing identity.
No, X inverse times X.
Times A inverse.
Oh, times A inverse. Oh,
Urutannya ngaruh bang.
urutannya ngaruh ya.
Yeah. Remember when we do this, it is B inverse times A, yeah.
Ya. Ya Delon.
Okay, so this is the eigenvalue. That's the matrix. Okay.
Berarti isn't that false?
What? Which one?
A inverse has the eigenvalues of
It's true lah.
Dua hal ya.
no, because
It's true.
that's the eigenvalue of A inverse times
Yes.
X inverse times A inverse.
No. It's the eigenvalue of A inverse.
Oh.
Eigenvalue of A is this one, right?
Oh, okay. But
Huh?
still need to review on
Yeah. Because when this is the eigenvalue, then it's just X inverse. Yeah. This is the matrix. This is the eigenvalue. If this is the matrix, then this is the eigenvalue. Okay. So sleepy. What happened?
Oh.
Huh? You're getting lost? Yeah. Yeah.
Yeah.
Okay.
Vector mapping.
Yeah.
EA.
You remember when we prove the power? You take the power of A, it becomes the eigenvalue. Eigenvalue, you take the power of it.
Yeah.
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 So this one also.
Proof that polynomial. Proof. Ini yang tadi. So we prove using the same.
Yeah, same method as this.
Yeah.
Yeah, you power it.
But power ya.
Yeah, using power. Okay, what about the summation of this? Plus.
The body matrix, the eigenvalue is
Oh.
per I
A to the power of M. Time identity.
A M kali A to the power of
Tadi gimana emang?
begitu pakai X kah?
Okay. Yeah.
Ya kan? X A to the power of M
X
inverse.
Yeah, that's for the power.
Ini
X A X inverse times A X
Bedanya ini.
inverse. Ada KM.
But then we have the km minus 1.
KM-nya dulu.
Polynomial matrix means
Power.
you still have to use the diagonalization, yeah. So you multiply left and right by the eigenvector. Because this is the same A matrix, the eigenvector between this one and that one, are they the same or not? The same eigenvector, right? So if I have the x multiplied by km a to the power of m plus km minus 1, and then plus k1a plus k0i times x inverse, what do we get? It is km
A to the power of m.
ml x inverse plus x, this is km minus 1, yeah, plus, and then in here k1 x x inverse plus k0 x I x inverse, yeah.
Isn't that supposed to be m minus 1? A to the m minus 1.
M minus 1, yeah, correct. So the result is what?
And x a to the
This is km
m tanda seru.
for m, okay, and then plus km minus 1 lambda n m minus 1. What else? Plus k1 lambda 1 up to lambda n plus k0 times 1 1. Okay, this is all diagonal matrix.
For X time A.
Why is lambda 0 is 1?
This is identity, right?
Oh, yes.
Ini nol sisanya.
Yes.
So the result is we have km lambda 1 power m plus km minus 1 lambda 1 plus k1 lambda 1 plus k0. This is for lambda 1. For lambda 2, you write the same thing. So that's km lambda n m minus 1 plus this is k okay. So you just replace I to here, you get that I. Okay. So the idea is we diagonalize the polynomial matrix, pre-multiply left and right by the eigenvectors. Diagonalize it. Okay.
Is this the answer?
Yes, that's the answer.
I don't think we need to all of
Yeah, we have to do all of them.
plus like add some all of them.
Yes, all of them. This one?
Bukannya cuman we just need to prove that the eigenvalues, the matrix has the eigenvalues of that.
Yes. Yeah, this is the eigenvalues.
Oh, sama ya. Sama ini.
Third,
Yeah.
X times A times x minus x inverse will be the yeah.
which we proved previously. Yeah, so we prove it just now in here, raising to power. Okay. Yeah. The last one, we run out of time, so you do it on your own, yeah.
Okay.
So I'll see you again on Thursday with a quiz.